Hey, 30-2s. In this lesson, what we're going to do is we're going to start combining probability with what we did in our last unit, counting methods. So it'll start to get a little bit more complicated here because we're going to go back and we're going to start talking about fundamental counting principle and permutations and combinations and combining it with probability. All right, let's take a peek here. So imagine rolling two different colored dice and listing all the possible combinations. So the first number listed is on the red die and the second one is listed on the blue die. So the first thing I want us to do here is I want you to hit pause on the video and I want you to fill in all of the different possible outcomes that you could get for this table. Okay, so take a minute, hit pause, and when you're ready, when you got it all filled in, come on back. See you in a minute. Okay, hoping you took the time to fill in that table. We're going to use it for the next few questions. So how many combinations did we find in total? Well, I mean, I can look at the table and say 36, but remember, the quicker way to find our sample space is to use the fundamental counting principle and to say there's 6 options for the first die and there's 6 options for the second, so 36. It's always good, especially in probability, to know how many outcomes we'll have. Okay, what we're going to talk about here is we're going to talk about our theoretical probabilities. So again, in theory means what should happen, which we know is different than what does happen, which is known as your experimental. So for part A says, let X represent the event of rolling a sum of 7. Let's go place an X over all of those outcomes. Okay, so a sum of 7. So that would give me a sum of 7, 7, 7, 7, 7, 7. Okay, so there's 6 ways to do that. So the probability of getting a sum of 7 then would be 6 over 36. Now, you can leave that as your answer, but you would always be nicer if you would simplify that. 1 over 6. B, let Y represent the event of rolling a sum of 9 or greater. It says put a Y over top of all of those desired outcomes. So 9 or greater. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 outcomes. So 10 over 36. Again, we could reduce that to being 5 over 18. Either way. Okay, I mean, that's an easy question, right? But again, we did include counting methods because we had to figure out the size of our sample space. Okay, complementary events. Remember what it means to be complementary. It means we're looking at two different things, what we want and what we don't want. Okay, a lot of people like to use the word opposite. We've got to be a little careful about using the word opposite, what I want and the opposite of what I want. You're usually fine if you think that way, but just be careful. Think about it as what I want and what I don't want. So A, let C represent the event of rolling doubles. Well, okay, I know there's only 6 types of doubles, right? So it's going to be 6 over 36. And I'm not going to simplify that for a reason here. B, let C prime, so remember C prime is our symbol for complement in 30-2, represent the event of not rolling doubles. Well, if there's 6 ways to get doubles, that means there's 30 ways to not get doubles. 30 over 36. Now notice what would happen again if we added these two numbers, these two probabilities, I should say, together. Well, 6 over 36 plus 30 over 36 is 36 over 36, or what the kids tell me, that's 1. Well, will that always be true? Well, 1 as a percentage is 100%. Look at what we have. We've got 100% of our outcomes accounted for. Will this always be true? Yes. An event and its complement must always account for all possible outcomes. So if I was looking at this Venn diagram here, if I had event A and A prime, the complement of A, Well, if I added these two things together, well, guess what? I'm going to get the entire universe, aren't I? So yes, a complement and the associated event must always give us 100% of our outcomes. Now, another way to do these questions without um, writing out the sample space or doing it in a different way is to do a tree diagram. Now, it's not our preferred way to do it. It's probably how we did it when we were little guys in elementary school. Okay, but I'll show you an example of what it looks like to do a tree diagram. There's nothing wrong with doing it. So what we're going to do here is we're going to have some cute little tigers here, and the family's going to have three cubs. Okay, so a litter of three cubs. And what's the possible number of outcomes we could have for the different genders? Now, the quick and easy way to do this would be to say, okay, for the first cub, male or female, second cub, male or female, third cub, male or female. I mean, that's 8. But one of the handy things to do here is to do a tree diagram. So what I would do is if I wanted to do a tree diagram, I would say, okay, I either start with a male or a female, and then I would just keep going. Okay, cub 2 is a male or a female, and a male or a female, and I've got to repeat. Now, this is where tree diagrams get a bit of a pain in the butt because this is already getting, pretty full on my page. So that's kind of the drawback to tree diagrams. Now my sample space, all I'm going to say is I'm just going to follow my order. I could have male, 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 or I could have male, male, female. I could have male, female, male, male, female, female. And I've just got to keep going here. So now I'm into the first cub being a female. Female, male, male, female, male, female, 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 male, and I'm out of room here because this takes so darn long to draw a tree diagram. Female, female, female. Okay, so the nice thing about drawing the tree diagram is it does give us that sample space, doesn't it? And we can see that it's still 8 possible outcomes, just like we got from using the fundamental counting principle. All right, now let's answer some questions. Determine the probability of the litter having exactly 2 male cubs. Okay, well, I see 1, 2, 3. So probability of 2 males is 3 out of 8. Easy when you got that sample space drawn, right? Okay, B, determine the probability of having at least 2 females. Okay, so P, at least 2 females. Well, what is that? That word at least means I'm going to get the probability I'm going to get 2 females, or the probability I get 3 females. And remember, the word or in mathematics means we're going to add. So how many ways can I get 2 females? Well, I see 1 way, 2 ways, 3 ways. And how many ways can I get all 3 females? Well, just 1 way. So if I wanted to show my work here, I would say 3 over 8 plus 1 over 8 is 4 over 8, or the kids tell me that's a half. Okay, so watch out for that idea of at least again. We saw that in the last unit. And determine the odds that at least one of the 3 cubs is a boy. At least one of the 3 cubs is a boy. So at least 1 male. Well, what I'm going to do here is when I want 1 male, okay, I'm going to do the complement. So what I don't want then is 1 minus the probability of 0 males. Well, there's only one way I can get 0 males. It's when I've got, right? I've got all females, don't I? That's 1 over 8. So the probability I get at least 1 boy or 1 male is 7 over 8. Now that's my probability. What are my odds I don't get a male? At least 1 male, I should say. Well, that's then 7 to 1, because in favor is 7 Total is 8, and that means there's one way I don't get a boy. Okay? Or I could have just gone up to my sample space here and just counted, right? Okay, so there's a tree diagram, which is a viable way to do a lot of questions. All right, last question. Let's mix in some probability and counting methods a little bit more here. So Joey and Steve are trying out for the basketball team, which consists of 13 players. There's 21 students, including Joey and Steve, trying out for the team. If the team is picked at random, okay, so if it's picked at random, I'm a combination because order doesn't matter. Okay, what's the probability that Joey and Steve make the team? So probability Joey and Steve. Well, what I've got here is how many ways can I get Joey and Steve? Well, what I'm going to say is it's a combination, and there's two of them, right? I need both of them. And then let's not forget the team consists of 13 players. So now I'm going to say there's 19 more students to select from, and we need 11 more of them. So that's the number of ways that Joey and Steve can both make the team. But it's a probability. So how many ways could I just make the team? 21C13. So when you're doing these questions, I like to break it up into two parts. Okay, what the question's asking for and the total amount, just like that. Okay, so I kind of just like to make it into almost an A and a B in my head. Okay, determine the probability that neither Joey nor Steve make the team. So not Joey and not Steve. Poor guys. Well, if I don't want either of them, to select 0. That means there's 19 more people to select from, but I need 13 of them in this one over 21C13. Okay, and now all you're going to do is put that in your calculator and find those numbers. And again, leave it as a fraction unless otherwise indicated, unless you're told to round. Okay, my friends, there it is, starting to get together with probability and counting methods.